All right, so we're going to close out this chapter by taking a look at mathematical induction, which is a technique for writing a proof. It's a way we could prove that something is true, say, for all positive integers, or maybe for all positive integers starting at some least element. So, you know, of course, one thing, if there's one, hopefully we get many things out of this course, but if there's one thing we get out of this course, I hope it's that we understand that an example is not a proof. And even if I were able to demonstrate something is true for the first 100 integers, or the first million integers, or the first, quadrillion integers, it does not mean that it's true for all infinitely many integers. And induction is really a pretty slick technique for showing that something is true for all integers. And here's how it works. There's two things that we put together that just sort of allow us to deduce that something is true for all positive integers or all natural numbers. The first thing we do, and this is the easy part, we show that it's true when n is equal to 1. We call this the base case. And usually it's not much more than just substitute in n equals 1 and do some arithmetic or algebra or something, and we just show that it's true. It's like plugging it in. Now, this next step, this is where the money is. This is what we call the induction step. And we show that whenever the statement is true for some n equal to k, and again, so we're not being specific, we're just saying, suppose it's true when n is k. If we could show that whenever it's true for n equals k, then it must also be true for k plus 1, then these things combined allow us to conclude that it's true for all natural numbers. It's like setting up an infinitely long string of dominoes. Because if we've established this induction step in the middle, then because it's true for 1, the induction step tells us it must be true for 2. And because it's true for 2, the induction step tells us that it must be true for 3, and so on. It just goes forever and ever. So we're going to do a couple of examples. We're going to show that the sum of the first n positive integers is given by the expression n times n plus 1 over 2. And one way to write that in terms of an equation is that if I add up 1 plus 2 plus 3 plus all the way up to n, it's equal to this fraction. So the value of n tells us where the sum on the left hand stops. So we begin with the base case. And so now we're just going to say if n is equal to 1, let's see what this equation looks like when n is equal to 1. So if n on the left-hand side, n tells us where we stop. If n is equal to 1, the left-hand side is just 1. I'm not adding anything to that, right? There's just one term. And on the right side, we have 1 times 1 plus 1 over 2. And this is true, right? 1 is equal to, we get 2 over 2. That's true. So the base case is done. Usually the base case is really simple. And then comes the fun part. Now is the induction step. So, the induction step always begins with the statement, let's suppose that this is true for some integer n equal to k. And that gets us something that we call the induction hypothesis. If it's true when n is equal to k, then the equation that results from that is 1 plus 2 plus 3 all the way up to plus k is equal to k times k plus 1 over 2. This sort of statement is called the induction hypothesis. And what's really important to understand is that this equation here, that's part of our induction hypothesis, we get this for free. We can use that whenever we like. So we've supposed that it's true for some integer n equal to k. Now we need to show that it's true when n is equal to k plus 1. Okay, well, when n is equal to k plus 1, this is, what I'm about to do next is pretty crucial. I'm going to work with what the left-hand side of the equation looks like when n is equal to k plus 1. So when n is equal to k plus 1, the left-hand side, and I'm just going to make a little note up here, I'm going to write it up in the margins. I do this a lot when I'm doing an induction proof, but I'm going to abbreviate LHS for left-hand side and RHS is the right-hand side. So when n is equal to k plus 1, the left-hand side looks like this. And now, if n is k plus 1, I don't stop at k, I'm going to add the next term, k plus 1. What I cannot do is say that this is just equal to what we get on the right-hand side when n is k plus 1 here. I need to show that it's equal to that. But a lot of the time, what I'll do is maybe a little bit of side work, just so I know what I'm looking for. So when n is equal to k plus 1, the right-hand side is k plus 1 times, and this would be n plus k plus 1 is k plus 2 over 2. And I'm just making a little note to myself because this expression right here, that's what I'm hoping that I'm going to get when I work with the left-hand side. Okay, and that'll kind of help me know when I'm done, when I've reached my goal. So, so here's what we have. Right, we have this sum. Now we can use this induction hypothesis. That equation in the blue box, we get to use that for free. So look what we have here. We have the sum of the first k integers as a part of that expression. So I'm going to use my induction hypothesis. This is equal to k times k plus 1 over 2. And then we're adding plus k plus 1. And that's k plus 1 over 1. I'm writing it that way because I'm going to get a common denominator. So now up in the numerator we've got k times k plus 1 plus k plus 1. Now there's a couple different ways you could go. Oh, not plus k plus 1, sorry, plus 2 times k plus 1. I almost left out that factor. I think that one thing we might observe here that makes kind of quick work of this is that there's a common factor. You know, like really what I'm doing here is I'm adding two products together, and those two products have a common factor of k plus 1. So I'm going to take it out. And then inside, I'm going to take, let's see, in the first product, I'm multiplying it by k, and in the second product, I'm multiplying it by 2. So here we have k plus 2. And this is the right-hand side. You know, if we go back up here just to what we were playing around with, so I wanted to know what the right-hand side looks like when n is k plus 1. That's what it looks like, and that's what we got. So 1 plus 2 plus 3, right, all the way up to k plus 1 is equal to k plus 1 times k plus 2 over 2. So we've shown that the equation holds when n is equal to k plus 1. So because the equation is true when n is equal to 1, and whenever it's true for n equals k, it must also be true for n equals k plus 1. It follows that this equation is true for all positive integers. So it follows that 1 plus 2 plus 3 plus n is equal to n times n plus 1 over 2 for all positive integers. Alright, so we're going to do one more of these. And we're going to show that the expression n cubed minus n is divisible by 3 for every positive integer n. So I'm going to just sort of restate this. And I'm going to say, we're going to show, if I want to show it's divisible by 3, I'm just going to restate it as saying that I want to show that it's a multiple of 3. So we're going to show that for all positive integers, n cubed minus n is some multiple of 3, so say 3 times m, for some integer m. Okay, so the first step, the base case, this is the easy part. We're going to show that it's true when n is equal to 1. So if n is equal to 1, this expression n cubed minus n is 1 cubed minus 1, which is 0, and that's a multiple of 3. It's 3 times 0. So the statement is true for n equals 1. Alright, so now comes the fun part, the induction step. We're going to suppose that this is true for some n is equal to k. So that k cubed minus k is 3 times m for some integer m. Okay, now what we want to do, so we get that for free, right? So remember that, we're going to have to refer to that at some point, but now we got to take a look at what this expression is when n is equal to k plus 1. So the expression that we're looking at k plus 1 cubed minus k plus 1. Now, a lot of times people are just chomping at the bit to say that this is equal to 3m or 3 times whatever, and we cannot say that yet. I'm hoping to show that this is a multiple of 3, but we don't know that yet, so all I can do is some algebra on this expression. I'm going to expand everything out, so k plus 1 cubed, this is k plus 1 times k plus 1 times k plus 1 minus k plus 1. And multiplying these two together gives us k squared plus 2k plus 1. And multiplying these together, you can make the little table or the grid to organize your work if you like, but this will be, let's see, k cubed plus k squared plus 2k squared plus 2k plus 1. Plus 1, oh, plus k plus 1. And then I'm going to distribute this negative sign like so. Now, because we're good, we have developed good algebra habits, it is probably our instinct to just combine all like terms at this point. But I don't want to necessarily combine all like terms. I want to get to a point where I can take advantage of my induction hypothesis up here. So I'm going to just note that I've got a k cubed and a minus k. So I'm going to gather those in the front. K cubed minus k. And then what's left over is 3k squared plus 3k, and then plus 1 minus 1, those cancel out. Now I'm going to use my induction hypothesis. This up here, that's 3m. And now, hopefully, we're all starting to get pretty excited because this is clearly a multiple of 3. Let's factor out a 3. Let's make it explicit. So here we have k plus 1 cubed minus k plus 1 is a multiple of 3. So, here's our conclusion. Since it's true for n equal to 1, and it's true for n equals k plus 1 whenever it's true for n equals k. Follows that n cubed minus n is divisible by 3 for all positive integers. Okay. So that's it. We did it. This is the end of Chapter 6. Please reach out with questions.